The James Webb Space Telescope, humanity's most advanced tool for exploring the cosmos, has delivered revelations that are reshaping our understanding of the solar system in profound ways. Once considered little more than a distant and frozen relic at the edge of the Sun's domain, Pluto has emerged in Webb's gaze as a surprisingly dynamic and mysterious world. Long relegated to the margins and dismissed after its reclassification as a dwarf planet, it is now capturing center stage as scientists uncover evidence of geological activity, atmospheric complexity, and even the potential for a vast, hidden ocean beneath its icy crust. These discoveries not only reframe how we think about Pluto itself, but also challenge our assumptions about the conditions under which life might arise, opening new doors to the possibility that habitable environments exist in the most unexpected corners of the universe. At the heart of this transformation is Sputnik Planitia, the bright, heart-shaped expanse on Pluto's surface that has become its most iconic feature. Once thought to be an inert plain of frozen nitrogen, this vast basin is now believed to conceal a subsurface ocean that could extend hundreds of kilometers beneath the ice. Insulated by thick layers of frozen material and possibly warmed by residual heat from Pluto's formation or the slow radioactive decay of isotopes within its rocky core. Such an ocean could remain liquid despite the extreme cold. If confirmed, it would provide an environment where the chemistry of life might be possible. This revelation undermines the long-held belief that habitable worlds must lie within the so-called Goldilocks zone of their parent stars. Instead, it suggests that warmth and energy can come not only from sunlight, but also from internal processes, meaning that worlds far from the sun, orbiting in darkness, could nonetheless harbor life. The surface of Pluto itself tells a tale of extraordinary complexity. Towering mountains of ice rise to heights that rival the tallest peaks on Earth. Their composition dominated not by rock, but by frozen water as strong as granite in Pluto's frigid climate. In contrast, the smooth plains of Sputnik Planitia show few craters, suggesting that the surface is constantly refreshed and reshaped. Scientists now believe that convection within the nitrogen ice acts much like the motion of a lava lamp, with slow but steady flows of material rising and sinking, erasing scars of ancient impacts and sculpting new patterns across the surface. This process indicates that Pluto is geologically active, a startling fact for a body so small and so far from the Sun. Much like the icy moons Europa and Enceladus, Pluto seems to possess a restless interior, hinting that the same fundamental forces shaping life-friendly environments elsewhere may also be at work here. Underlying this activity is the slow but steady heat generated by radioactive decay deep in Pluto's core. While modest compared to the immense power driving the gas giants, it may nonetheless be sufficient to maintain liquid water beneath the ice for billions of years. On Earth, ecosystems thrive around hydrothermal vents deep in the ocean, independent of sunlight and powered instead by chemical and thermal energy from within. The possibility that similar conditions exist beneath Pluto's surface, fueled by internal heat and shielded by an insulating shell of ice, is one of the most tantalizing implications of Webb's data. If true, then Pluto could join the short list of worlds within our solar system that may host environments suitable for life. Pluto's atmosphere adds yet another layer of intrigue. Composed primarily of nitrogen with traces of methane and carbon dioxide, it is astonishingly thin by earthly standards, but far more complex than once believed. Its behavior is linked to Pluto's elongated orbit, which takes it on a 248-year journey around the Sun. When the dwarf planet swings closer to its star, the weak sunlight is sufficient to warm the surface ices, causing them to sublimate and thicken the atmosphere. As Pluto drifts farther away, these gases condense and fall back to the surface, creating a cycle unlike anything seen elsewhere in the solar system. This cycle, in turn, allows researchers to study atmospheric dynamics under conditions that push the boundaries of planetary science, offering insights that may even apply to exoplanets with extreme orbits. Webb has also revealed delicate layers of haze extending hundreds of kilometers above Pluto's surface. These hazes, born from the interaction of ultraviolet sunlight with methane, give rise to tholins, complex organic compounds that settle across Pluto and its largest moon, Charon, painting them with reddish hues. The importance of tholins cannot be overstated. On Earth, similar prebiotic molecules are thought to have played a role in the origins of life. While tholins themselves are not alive, they are chemical building blocks that, when combined with water and energy sources, can evolve into more complex organic structures. If tholins are interacting with Pluto's possible subsurface ocean, they may be catalyzing the kind of chemistry that leads toward biological systems. In this sense, Pluto may represent a natural laboratory where the first steps toward life are quietly unfolding beneath a frozen crust at the edge of the sun's influence. Adding to the mystery is Pluto's unusual relationship with its largest moon, Charon. Nearly half Pluto's size, Charon is so massive that the two bodies orbit a shared center of gravity located outside of Pluto itself, making them more of a binary system than a traditional planet-moon pair. This intimate relationship has profound consequences. The tidal forces exerted between Pluto and Charon generate heat in their interiors, adding another potential source of energy that could sustain geological activity. Charon's own surface reveals deep canyons, ridges, and polar patches of reddish coloration that suggest a complex history linked to Pluto's. Scientists now believe that material, perhaps including organic compounds, may be transferring between the two worlds, creating a chemical exchange that could evolve over time. If so, Pluto and Charon may not only orbit together, but also share a dynamic, interconnected system where chemistry flows between them, increasing the likelihood of complex organic processes. None of this would have been possible without the James Webb Space Telescope. Equipped with powerful infrared instruments, Webb can peer through Pluto's icy shell, detect subtle variations in temperature, and analyze molecular signatures with a sensitivity unmatched by earlier missions. While New Horizons provided breathtaking close-up images during its 2015 flyby, it could only scratch the surface. Webb's data go deeper, offering hints of Pluto's hidden ocean, the activity of its atmosphere, and the presence of organics that may hold the key to understanding prebiotic chemistry. In this sense, Webb has not only revived scientific interest in Pluto, but elevated it